Okay, then we will start. Okay, welcome everybody to a new Origin seminar. Today we have a talk by from Kamber, who is a Sagan Fellow here at the University of Arizona. She first did her undergrad here at U of A, then moved to Michigan, and then for a second came back again in 2018. And she's working on the evolution of gas material and disks. So, and today she will give a talk about GM Aurigae. Please try to turn off your camera and your microphone to decrease the bandwidth. And also, please keep your questions to the end, unless it's a very urgent question about a current slide, then please ask that question in the chat. Okay, thank you.
All right, thanks, Sebastian. And thank you everyone for coming, especially for those of you who have already seen several hours of protoplanetary disk talks at the HL conference this morning. So I'm going to be talking about some recent work that I have done looking at the GM Aurigae protoplanetary disk, trying to constrain some of its basic physical properties. So the mass of a protoplanetary disk is one of the most fundamental properties that the disk has, but it's also something that is extremely difficult to constrain, and that is because the majority of the mass in protoplanetary disks is in the form of H2 gas, which does not emit for the vast majority of conditions within disks. So we can't see it. Less than 1% of the mass is going to be in solid dust particles, which we can observe as long as they are smaller than centimeter size. And then less than 0.01% of the mass is in other gas phase species, with the molecule CO being one of the most abundant. So with ALMA, we have now observed a large number of protoplanetary disks, both in dust and CO. And something that we're finding pretty consistently is that the CO is underabundant relative to the dust. And it's difficult to tell exactly why this is. It's either due to a low total gas mass, which is the top x-axis on this histogram, or it's due to a low CO abundance in these disks, which is shown on the bottom axis. But either way, the majority of protoplanetary disks are significantly different from the material in the ISM. Now, it can be difficult to determine which of these two scenarios is correct because of how we measure gas mass. So typically, we either start with an observation of the dust and assume that the continuum flux is proportional to the dust mass, which is generally a good assumption as long as this emission is optically thin. We then assume an H2 to dust ratio, typically 100, to get the total gas mass. Or we start with CO observations and we say that the CO column is proportional to the integrated intensity. Once again, only a good assumption if the emission is optically thin. And then we assume a CO to H2 ratio of 10 to the minus 4, correcting for freeze out and photodissociation to get a total gas mass. And basically, these two ways of getting mass measurements are disagreeing with each other, causing this discrepancy. And we need some additional tracer in order to break this tie. So this additional mass tracer does exist in 3 protoplanetary disks, and that is the H2 isotopologue HD, which is much more closely related to H2 than either CO or dust. This has been detected in 3 disks using Herschel. And if you use these spatially unresolved detections to get the disk gas mass, you find CO abundances that are between a factor of a few and over 2 orders of magnitude below the ISM abundance, which means that in every disk where we have this alternative mass tracer, it is the CO and not the total gas, which is missing. Now, a word on the utility of HD as a mass tracer. If you're trying to take your HD flux and convert it into a gas mass, you'll find that there's a very strong degeneracy between the HD abundance that you assume and the gas temperature that you assume. So here we have a grid of HD fluxes as a function of gas temperature and gas mass, and you can see that anything along this line would match what we observe for the disk TW Hydra. In addition to that, HD is only going to emit at temperatures greater than 20 K. So you also need to know what fraction of your mass is cooler than 20 K. So basically, any mass that you derive from HD is going to be very sensitive to the temperature that you assume. Now, if you're using HD to get, one more complication. HD also self-shields from photodissociation lower in the disk than H2. So if you are getting HD emission from the region between where H2 self-shields and HD self-shields, then you're not going to necessarily be sure of the abundance ratio of the two species to convert from HD mass to total H2 mass. Things are a little bit less dire if you're using HD to get a CO abundance relative to H2 in conjunction with CO observations. And that is because CO freezes out at 20 K, so you don't have to worry about the mass that you're missing when HD does not emit. And in addition, HD and C18O self-shield at similar heights, so that's another thing that you don't have to worry about as much. So basically, HD traces CO over H2 more directly than it does the total gas mass, and it is very sensitive to temperature. So because of this, I led a project several years back now using resolved observations of CO isotopologues in TW Hydra to get a radial temperature profile for the HD emitting layer in this disk and use this to constrain the total gas mass. So we used our CO surface density from the optically thin CO lines and our temperature profile from the optically thick lines, combined with our HD detection from Herschel to get a warm gas mass of 5.6 times 10 to the negative 3 solar masses. And if we assume, based on models of this disk, that 10 to 20% of the disk is warmer than 20 K, this corresponds to a total disk mass between 0.03 and 0.05 solar masses. So this is about half the total mass estimate that was predicted for this source by Diana Powell in 2017, using dust emission at different wavelengths to calculate dust drift timescales and then back out a mass from that. However, this particular technique does not yet consider things like substructure in the disk, which would affect your drift timescales and overpredict the total gas mass. So I think as long as we are under what I think of as an upper limit, we're doing pretty well. In addition, because we now had an idea of the amount of mass as a function of radius, we could plot the CO abundance relative to H2 as a function of radius, and we found that everywhere in the disk, CO is underabundant compared to ISM values by about 2 orders of magnitude. We do see some return of CO inside the CO snowline, but it's not nearly enough to explain the overall low values. Additionally, we could tell a little bit more about what's going on with CO in this disk from our temperature profile. So in the outer disk, we measure a pretty constant temperature of about 21 K. And this is because the bulk of our emission is coming from the CO gas layer right above where CO freezes out onto ice. So this is telling us the temperature at the CO snow surface, which is about 21 K, corresponding to a binding energy onto the grains of 960 K. We can then use this information to predict the location of the midplane CO snowline, which we are not directly probing with these observations. So to do that, we just solve for the temperature in the disk where the rate of freeze out on to grains equals the rate of desorption for CO off of grains, using a binding energy and a CO density that we get from our observations. We then compare this to a model of the midplane temperature. Here we're using a model of the TW Hydro disk from Lecules et al. 2015. And we predict that the midplane snowline should be between 18 and 25 AU. So in the next year, my collaborator Coco Zhang obtained new observations of the extremely rare CO isotopologue 13C18O towards this disk. And her analysis was able to show that while even C18O is optically thick in the inner disk, coming from about 1 scale height above the midplane, the 13C18O transition is really probing emission from the disk midplane itself. She modeled the CO columns and was able to identify the location of the midplane CO snowline as 22 AU, right in the middle of the range that we predicted. So if we assume that all disks have a low CO abundance relative to the total gas, we can take the histogram that I showed earlier and plot it a little differently. So now we have CO relative to H2 along the y-axis, and then the x-axis is the age of the system. So individual points are showing the values and uncertainties for a single disk. And then these two dashed lines show the range of values for disks in the Lupus and the Chameleon star-forming regions. And the point that I really want to make here is that you can get anywhere from no depletion, factor of 10 depletion, even a factor of 100 depletion by 2 million years. And how much depletion you have is going to vary from disk to disk. So it's very difficult to just a priori correct for the amount of CO depletion to back out a gas mass. If you look at very young systems that are still embedded in their infalling envelope, those are the ones shown in red here, then there seems to be no variation from the range that we see in the ISM, which tells us that gas phase carbon depletion happens early. So for systems like TW Hydra, which are viewed pretty much face on, we can get an idea of the radial variation in the system, but it's difficult for us to understand the two-dimensional distribution of things like CO gas. However, if your disk is more inclined, you can actually directly image the CO surface. And this is something that was demonstrated by Christoph Pint in 2018 using the Protoplanetary disk IM loop. So what I'm showing here are CO channel maps, which is just the emission broken into velocity bends. And you can see that the location of the peak intensity changes as you move in velocity bend due to the Keplerian rotation of the disk. You can also very clearly see emission from the upper surface of the disk and emission from the lower surface of the disk. The reason that you don't see much emission between these two layers is because CO has frozen out onto grains in the cold disk midplane. So what Pint et al. Did is traced out the location of these emission surfaces, and because the inclination of the disk is known, they were able to deproject this and get the height of the emission above the disk midplane. Not only that, but they were also able to measure the temperature of the emission as a function of height. So this is the radial temperature profiles for the various CO surfaces. And for surfaces that were coming from right above CO freeze out, they once again find a temperature of about 21 K. All right, so that brings me to the ALMA large program, Molecules with ALMA at Planet Forming Scales, or MAPS. This is a large collaboration that I am part of, PI'd by Karin Oberg, Viviana Guzman, Catherine Walsh, Yuri Akawa, and Ted Bergen. And this large program is a survey of molecular lines towards 5 protoplanetary disks conducted in ALMA bands 3 and 6 with a high spatial resolution, so 0.15 arcseconds in band 6 and 0.3 arcseconds in band 3. And there are a multitude of projects that are coming out of this program. But for this talk, I'm just going to focus on the results that we get from the CO isotopologues, which are shown here with some interesting features marked by one of our collaboration members, Charles Law. All right, so one of the goals of this program was to map the CO gas distribution from a combination of observations and thermochemical models. This is a project that was led by Coco Zhang, where we started by building a model that would match the SED in RADMC3D to nail down the dust structure. This is then piped over to a thermochemical code called RAC2D to generate the temperature and molecular distribution maps. The CO abundance is then modified after this and then put back into RAC2D to run radiative transfer. Then the models are compared to observations, and this process is iterated, modifying physical parameters and CO abundance until there's good agreement with the observations. So these are the results of the best fit model from the Zhang et al. Project. So this is showing the CO depletion factor as a function of radius and each disk, as well as the location of the midplane CO snowline in each model. So these best fit models are based on being able to reproduce the C1802 to 1 emission in both intensity and height in the disk. And you'll notice that all of the disks have CO abundances below ISM values. However, the T-Tauri disks around low mass stars tend to have lower CO abundances than the 2 disks around higher mass Herbig stars. So this is giving us a lot of information about what is going on in these protoplanetary disks, but it's only focused on fitting one of our CO lines. And we have a lot more information than this. In particular, GM Aurigae is one of the 3 systems with an HD detection. So what I've been doing as part of this collaboration is building a more in-depth model of GM Aurigae that is able to reproduce the HD flux from Herschel, which was originally analyzed by McClure et al. In 2016, as well as all of the CO isotopologue transitions observed as part of the MAPS program, and an additional 5 transitions from my own ALMA program at slightly lower resolution. And the goal here is to, by fitting these 11 CO lines and the HD flux, be able to generate maps of the H2, CO, and gas temperature distributions. So while in the CO modeling process, the CO abundance was modified after running the chemistry. When modeling both the HD and the CO, we modified the CO abundance before running the chemistry. And this is because since this is a thermochemical code, changing the CO abundance is going to change the gas temperature. And as I mentioned earlier, understanding what your gas temperature is really important for backing out a HD abundance from HD emission. All right, so a little bit about the actual GM Aurigae disk. This is a 3 million year old transition disk system where we quite clearly see an inner cavity in the dust continuum. It's about 159 parsecs away, I think 158 now with Gaia DR3. The dust disk extends to about 260 AU. The gas disk is much larger, extending out to about 650 AU. And we see these beautiful rings of dark and bright emission in the millimeter and centimeter continuum, which have been modeled quite successfully by Macias et al. In 2018. And so when starting to build the model for the GM Aurigae disk, we use the Macias et al. Dust substructure model as a starting point. All right, so we started with the best fit model parameters from the Zhang et al. Analysis. And from this generated radial intensity profiles. So the blue here shows the radial intensity profiles for the observations and the 1 sigma uncertainty. And the black lines are for the model emission. So this does a pretty decent job of tracing the emission, particularly for the C18O. However, there's a couple places where things aren't excellent. So for instance, we are severely under predicting the amount of 12 CO2 to 1 emission in the inner disk. The observed HD flux is 2.5 times 10 to the negative 18 watts per meter squared, and we're getting 2.9, which is a little high, but still within the uncertainties on our measurement. However, we also have some information about the vertical distribution of CO for the 12 CO 2 to 1, as well as the 13 CO 3 to 2 and 2 to 1. The other transitions are too weak for us to do this sort of analysis. But here we have extracted the emission surfaces using the Python package disk projection, which was developed by Richard Teague and uses the method from the Pint et al. 2018 study. So here, once again, blue is observations with uncertainty and red is the model. And in this model, the 12 CO emission surface is too low in the disk, pretty much at all radii compared to observations. For the 13 CO surfaces, we're doing a decent job of tracking in the inner disk, but we are under predicting the surface in the outer disk. So to improve this, we had to play around with model parameters, which took a very long time, but I'm sure you don't want me to go through all of them. So I'll just skip to what ended up being our best fit model. And so to improve on the original model, what we had to do was increase the gas temperature for radii inside of 32 AU and for Z over R greater than 0.1. So this allowed us to increase the 12 CO temperature without over predicting the flux from the 13 CO and the C18O, which we were already matching pretty well. Additionally, we had to adjust the surface density of the disk in the outer regions of the disk in order to raise the emission surfaces of the CO lines. So these are the radial profiles that we got after making those corrections. And you can see that we are now within 1 sigma of the observations for pretty much every transition at every radii. The HD flux only changed a little bit from 0.9 to 2.9 to 2.8, which does get us a little bit closer to what is observed and is still within the uncertainties. For the vertical emission heights, here is what our initial model looked like, and here is what we're getting in our final model. So in our model, the emission surface is still slightly lower than in the observations, but we are getting within the uncertainties for the observations, and in particular are doing a really good job matching the 13 CO2 to 1. All right, so for the best fit model, the properties were a total disk gas mass of 0.25 solar masses. This is compared to the mass of the central star, which is 1.1 solar masses. And while the disk does extend out to 650 AU, 87% of this mass is at radii smaller than 200 AU. And the HD emission is actually coming from mostly these inner regions as well, with 93% of the HD emission inside of 200 AU. And the reason that we have the HD preferentially tracing the inner regions of the disk is because this disk is also very cold. So 30% of the disk mass is cooler than 20 K. And we need the disk to be cold to agree with the CO line observations. So just as in the Pine-Tedal paper, not only were we able to extract CO emission heights, but we were also able to extract CO emission temperatures from the 12 CO and the 13 CO 2-to-1 and 3-to-2 lines. So here the measured temperatures are shown in circles, and then the background is our model. Here we're not, the disk appears to be too warm. However, these measured temperatures are less than 20 K, and CO should freeze out at temperatures less than 20 K. So I think that this is probably coming from optically thin lines that do not provide a good measurement of the disk temperature. But where the lines are optically thick, we're doing a good job of matching the gas temperature. So because we need a cold disk to match the measured temperature from CO, we need to have a very high mass disk in order to match the observed HD flux. All right. We also can look at the CO abundance in our best fit model. So here we have the two-dimensional map of the CO abundance relative to H2. And you can see that pretty much throughout the entire disk, the CO abundance is lower than the ISM value. We can also plot the total CO depletion as a function of radius, and we find that throughout the disk we have between a factor of 10 and factor of 100 CO depletion. All right, so this is a massive cold protoplanetary disk. And you might be wondering whether or not this disk is stable against gravitational collapse. So we can check that by calculating the Toomre Q parameter using values from our best fit model. So here I show the calculated parameter using temperatures in the midplane for our model zoomed in on just the inner 300 AU. Now, typically you need a Toomre Q value less than 1 to be gravitationally unstable if you have a geometrically thin disk. However, if your disk is not well approximated by this geometrically thin assumption, then it's been shown that instabilities can start to occur for Q values as high as 1.7. And you can see that we do have Q values dipping below 1.7 between 70 and 120 AU. The gray shaded regions here are marking the dark lanes observed in the dust continuum. So this place where we are dipping below our Q of 1.7 actually corresponds to one of the bright rings centered at about 84 AU that is seen in the dust continuum. And what's really driving this low Q value is the low midplane temperature, which is shown here in this region, and it is low because of the high concentration of dust particles. Okay, so is there any actual observed evidence that this disk is unstable? At this point, we should really talk about the elephant in the room, which is the 12 CO emission. So I think probably one of the most exciting results to come out of this ALMA large program is the 12 CO emission in GM Aurigae, where we see these really beautiful spiral structures, which are marked here. This is an analysis that is being led by Jane Huang. And her analysis of the kinematics of these non-axisymmetric features shows that the kinematics are actually inconsistent with a gravitational instability. However, they are consistent with what you would expect from late stage infall onto the disk, either from a parent cloud or a residual envelope. And if you look at the large scale emission in this region, here shown in 500 micron dust emission from Herschel, you can see that there is some nearby emission, though like extremely clear filaments connecting GM Aurigae to this emission are not super, super obvious. All right, so this spiraling emission is not due to gravitational instabilities, but if we take a closer look at this ring in the continuum, which was done in an earlier paper this year, also led by Jane Huang, we can see that this ring appears to be wider along the minor axis of the disk than along the major axis. So the Huang et al. Analysis showed that this is not an imaging artifact and that it can be explained either by non-axisymmetric structure from a perturber or by vertical structure in the dust. Now, the tomb ray Q value that we're getting here is due to a low disk midplane temperature. And there has been some recent work showing that if you have a planet migrating through a disk, it can locally heat the disk and suppress spirals in regions that would otherwise be gravitationally unstable. Our observations probing the temperature of this disk, however, do not reach down to the midplane at 84 AU. So this midplane temperature that we're measuring is based on our best fit model and not extremely strongly constrained, or at least not directly constrained by the observations. So I don't think that we have enough information to say anything conclusive about the stability of this disk. However, we are starting to amass multiple hints that something interesting is going on around 84 AU. All right, so to summarize, as part of the MAPS large program, I have built a thermochemical model to match emission from HD and 12 resolved transitions of CO isotopologues for the disk GM Aurigae. Our best fit model indicates that this is a massive disk with a mass of around 0.25 solar masses. It's also extremely cold, with 30% of the disk cooler than 20 K. It is depleted in CO throughout the disk by 1 to 2 orders of magnitude. There's some evidence for late stage infall onto this disk that is clearly a transition disk, and it's possible that it is borderline unstable at 80 AU. All right, thank you all.
Thank you, Kamber, for a great talk. Everybody, if you want to, you can unmute yourself and give an applause. Yeah, I think we have some questions. I think Caitlin raised her hand first.
Hey, Kamber, this is really, really exciting stuff. So I just wanted to sort of probe a little bit more about the modeling that has or hasn't been done related to the instability. But as you point out, right, this boundary at which instability typically arises is a bit fuzzy. It depends on the aspect ratio of the disk and the disk mass and whether or not you're talking about axisymmetric or non-axisymmetric modes. And I guess the dust structure looks very, pretty darn axisymmetric. I just, the wobble of the ring, I don't think is really characteristic of the higher order modes you see from gravitational instability. So I'm just wondering, has anyone done a full numerical model and said, if you put in this temperature and density profile, what would you get? Because I would suspect with much of the disk at the Q values you've calculated, you would see larger scale spiral modes.
Yeah, so as far as I'm aware, there has been no dynamical modeling specifically trying to match this system. These are results that have really only come out within the collaboration within the last 2 weeks. So there hasn't really been time.
Okay.
But so Another thing, you mentioned that you would see lots of spirals, right?
I didn't say lots, but some.
But some,
perhaps.
right?
Yeah.
And we do see spiral-like features in the 12 CO at large radii, and maybe in the 13 CO a little bit, but none of the other lines that we have observed have shown any sort of non-axisymmetric feature, not just for the CO, but for any of the lines that were included in this survey.
Right. And I guess I'm saying I think it would be very challenging to have the dynamical environment associated with gravitational instabilities or even strong self-gravity coexist with that very axisymmetric ring. Mm-hmm. So I guess rather than me asking, where, like, saying there should be spirals, I'm saying, what are the possibilities for it not being gravitationally unstable, for Q to be higher than you've otherwise guessed?
Yeah, and I'm not an expert on dynamical modeling at all, but I will say that this is really being driven by the low midplane temperature in our model at this radius. Our model does not assume any like gas surface density substructure in the same way that it does the dust surface density substructure. So that could be changing temperature values. There could be some other heating or cooling mechanism that we're missing that would result in a higher midplane temperature. So I think some follow-up work that I would really like to see done is using something like 13C18O or C17O to try to get down to the midplane at 80 AU and directly measure the temperature there.
Yeah, because I mean, how hard would it be to change the temperature by? I mean, I guess it's hard to change the temperature by enough to solve the problem, which makes me worry about the density rather than the temperature. What are the prospects for that being, the models failing to capture the gas density properly?
Right. So most of our gas density is coming from the HD. And like I said, HD isn't probing anything that is cooler than 20K. And I believe that the midplane at 80 AU, we are cooler than 20K. But we do have some constraints on what the density is higher up in the disk at 80 AU in order to get the correct heights and line strengths for the CO emission. So I'm not going to say definitively that there's no way that the surface density could be extremely different. But I suspect that while this is not it's possible that there's a better model out there. I just, didn't have time to run a million. But I think we're in the ballpark. So factor of less than 2, I would say.
But that's, I guess, so for temperature, right, it's hard to change things by a lot. But a factor of 2 in density takes the disk from being quite likely unstable to not even to very unlikely to show structure, right? So you don't need that much. So it wouldn't take much to change that answer a little bit.
Yeah.
Thanks.
Okay, I think we also had a question from Andre.
Hi, can you hear me?
Yes, I can.
Yes.
Hi, Kamber. Nice. Thank you for the nice talk. I have actually two quick questions. One is about the spiral you show here in 12CO. So you show that 12CO is optically fixed. So to some large radius. The fact that you see structure in 12CO is because these are structure in the temperature, or is because at some point the 12CO becomes optically thin and there's a structure in the density? So can you comment on that? The other quick question is, if I can, so do you remember what is the mass you get from the dust and how that compares to the mass you get from the gas?
Yes, okay. So first, what is causing the structure? So this is, I think that we expect the 12CO to be optically thick out to extremely large radii, though of course the 13CO only extends out to like 300 AU. So we can't do like the ratio of the lines to measure it. But we do think that if I can, yeah. All right, so this is showing some of the channel maps from the 12CO, once again from Jen Huang's paper. And these are probably my favorite channel maps to click through, because you start with what looks like a pretty basic Keplerian disk, and then once you get to the systemic velocity, you start seeing that we have emission at non-disk locations that is moving around this vicinity. So I don't know if that quite answers your question about if it's a temperature or a density thing, but I do think that we have some non-disk emission that is causing these structures. So, and then your second question was, what is the dust mass? So we used the dust mass from the Macias et al. Analysis, changed slightly because we changed the dust composition properties. But these are the values for our best fit model. So it's like 6 or 7, 10 to the negative 4 solar masses in dust.
Okay, thank you.
Mm-hmm.
And then we have a question from Christopher.
Yes, actually, my question, well, thank you very much for the very nice talk. My question was just answered in that second part of Andreas.
Okay.
So I'm good.
All right.
And Joan also had a question.
Hi, Kamber. Thank you so much for the terrific talk. Very really interesting insights into a really popular object. I had a couple questions. One was, you mentioned that to get a good fit to the data, the model, you had to increase the temperature at high Z/R and at small radii. What do you think is the source of heating that is sort of missed in the model? That's my first question. I don't know if you want to, maybe that, I'll just ask that first.
Yeah, so I'm not entirely sure. I will say, I don't think I said this in the talk, but we had to increase the temperature by a factor of 10, which, I mean, we were still only in like at 80K. So it was like 80K to 800K, which is a lot, but better than going from like 800K to 8000K. We've talked a little bit about this within the collaboration. There might be some sort of like heating due to accretion onto the central star, maybe. There's also this, like there's two ways to make emission stronger, right? You can increase the temperature or you can increase the mass. So it could also be that we need more mass there, but then you also need to increase the mass closer to the midplane, which is going to affect the lines that we're already fitting. So that's why we went with temperature without having an excellent explanation as to why that would be.
Sure. I guess my other question is a little related. I think you said that some of the reason for the high temperature is driven by the HD flux. And well, you showed a little bit of it, and I'm not an expert on that observation. In fact, that might be the first time I saw it, but it looked like there were other features there next to the HD line. What do you think is the uncertainty on the HD flux, and could other measurements, I mean, how much better would measurements have to be to sort of pin that down, if that makes a difference?
Yeah, so the uncertainty on the flux is 2.4 10 to the negative 18, and the uncertainty is plus or minus 0.5 10 to the negative 18, right? So it's about like a fifth, if I'm doing math right in my head, which I might not be. And we are slightly over predicting the flux, but we're within the uncertainty. So if we got a tighter constraint on that forced us to have a weaker HD emission, and the 2.8 that we're getting right now was no longer within the uncertainties, then that would drive down the mass a little bit. Not to like 0.02, but like maybe 0.1 0.15.
Okay, yeah, that sounds good. It's kind of related to Caitlin's point that a factor of 2 could make a difference. I guess maybe that's a reason to put a little work into HT, not necessarily from you, but just that the community could invest a little bit in that to kind of resolve that, perhaps.
Yeah, though we don't currently have any instruments capable of observing HD, so it'll have to wait unless we can come up with like better analysis techniques for the archival Herschel detection.
Right. Okay. Thanks.
Mm-hmm.
Yeah, we got one more comment in the chat from Caitlin. If you can comment on whether the model enforces HSE. I'm not quite sure what that means, but.
Whether or not the temperature and the scale height in the disk are consistent with each other? Is that what you're asking?
Just, yeah, is your model enforcing hydrostatic equilibrium, right?
It is not.
Ah, I see. So how far out of equilibrium are these disks in the vertical direction then?
I have not checked. Probably they're not in equilibrium. The problem is that because the thermochemical models that do enforce hydrostatic equilibrium take so much longer to run, when you're trying to fit as many observations as we are in this program, it becomes quite quickly an intractable problem.
Sure, no, I know, I can certainly imagine, I guess, but just in terms of knowing, how you assess this, this very large change in the temperature that you're getting or these densities, it might be worth knowing sort of how far outside of hydrostatic equilibrium the model is as a function of radius, and if there's if the problem shows up in the region where where you're predicting instability, or the other regions, I don't know, it might be interesting to know.
Yeah, that is definitely something that I should go back and do before I submit this. Thank you.
If I get to follow up on that, do you remember what is the scale height at 80 AU? That would kind of perhaps address. Because you have a plot that you show Z as a function of R in one of your slides,
right? So let's see. We can look at probably this plot, right? So this will give us the height of the 12 CO emission as a function of radius, 80 AU, and we're at about what, 25, 30. That's of course not the same thing as the gas scale height. So I guess we could look at the 2D gas distribution and try to back that out. But this is a pretty flared disk.
It's about 10%, I think.
Mm-hmm.
I mean, looking at this.
Yeah, that was one of the things that we had to mess around with in order to fit the.
Which seems pretty thick, but it might be more, yeah. Seems pretty thick for such a low temperature.
Mm-hmm. Well, it's also there's a lot of mass there too, right? Which would help cool it down. But yeah, it's a very complicated problem.
We have a question from Yancy.
Yeah, so to constrain the very high temperatures in the innermost region of the disk, could you try to go after even higher J lines of CO, like do something in band 9 with ALMA to try to constrain that very innermost high temperature region?
I do have band 9 observations. So we have the 13CO, the C18O, and the C17O, 6 to 5, but at a fairly low signal to noise, and I'm very lucky to have gotten anything at all because band 9. So I didn't look at the radial temperature profiles for the 6 to 5 lines. I just tried to do the surface extraction, which they weren't high enough secondary noise to do. But certainly we could do like a radial temperature measurement from the 1306 to 5 like we did with TW Hydra and see what we're getting from that.
Okay, if there are no more questions, I would like to thank Kamber again for a nice talk. And I hope to see everyone again next week at our last Origin Seminar talk of the year.
Thank you.
Thanks.
Thank you. Bye.
Thanks.